Hello, and welcome back to another episode of the Oxford Online Maths Club. Pausing slightly, my name's James, and I'm joined this week by Lily.
Hi, I'm Lily, and I'm a current student doing maths and philosophy here. Philosophy is important. And you might have seen me in the open day last week.
Yeah. Oh, is it like? Oh, is it?
Last
Yeah.
week? The week before?
Might have been 2 weeks. Might have been three. Oh, who knows? Time flies. Yes, Lily's superstar ambassador, who's here today because we're going to talk about random walks. So we're joined by Lily on screen. Thank you, Lily. And in chat, I believe it is Callie again. Superstar chat moderator who is running chat. You could be in chat as well if you're watching live, like this anonymous person who says, "Hello, everyone." Hello, anonymous person. Chat is also where we run things like polls, if we've got any polls. At the moment, I've just got this one about how was your day. Lily, if you don't have to answer, but how was your day today on a 5-star scale?
I would say 4.
Oh, okay.
It's
What's
pretty good,
that's a
but
pretty good day.
yeah.
Have you been up to anything fun today?
Um, Not really, but like I don't have lectures in the morning today, so it's a good day.
Right. I had a session this afternoon, meeting some of my students to talk about second year students to talk about minimizing functions. We're getting really good at minimizing functions in second year. People watching might be doing A levels or equivalent, where you learn a bit about minimizing functions later on. Good. Right. Hello in chat to Hector and Aaron, who says they were previously anonymous, now Aaron, and also Joe, who remembers Lily from some sort of an open day, maybe. Chat is having, at the moment, a 4.5-star day, which is pretty good. While you're joining and while you're letting us know how your day was, do let us know how your day is going in chat as well, if you like. Here's the question that we're going to be thinking about today. It goes like this. Imagine a counter. I suppose I mean something that counts like whole numbers that starts at 0 and each and every second either goes up by 1 or down by 1. So it starts at 0 and you come back a second later, it might be at 1 or it might be at -1, or with equal probability. I need to put that in, that's very important. Click. Equal probability. So it's like a 50-50 thing. Maybe a coin flip happens behind the scenes. Either it goes up by 1 or it goes down by 1. That'll stop at 10 or -10, or when you stop it. So you get some choice in this game. And the question is, can you play strategically in the game to maximize the number that you get? We want large numbers. You might recognize this kind of framing of this kind of random thing that goes up and down. I don't know. Let's put Lily on the spot. Lily, what sort of thing does that remind you of? If I have something going up and down. Well, it's a hard question for you because you've done courses on random things that go up and down.
Yeah, how much should I say?
Well, I was hoping for like a real world thing.
Well, imagine you're gambling, which not recommending anything, but your money goes up or down.
Yeah, good thing to think about, because I've remembered, yeah, possibly people watching are under the age of 18 or whenever you can gamble in different countries. But sure, gambling is a thing where your amount of money might go up or down. I suppose maybe we could say board games as well. Snakes and ladders.
Yeah.
It's a pretty timid version of snakes and ladders, where you're just going like up one square or down a very short snake, down one. Hector in chat says it makes think about coin tosses. Yeah. So there's something about Hector's on some advanced gambling strategy. You've made me really cautious now, Lily. What's the philosophy? We'll get there. Anna says hello. Hello, Anna. Right, good. Okay. That's the game. It's going to go up by 1 or go down by 1. No staying the same. I've built this in Desmos so that we can play along. So we've got a Desmos version. So maybe your strategy. You can tell me your strategy in chat now if you like, or if you're Lily, you can tell me your strategy out loud in a second if you like. But you also get a chance to test it around here. Okay. Quick discussion of what your strategy might look like. It's going to start running in a moment. It's going to go either up by 1 or down by 1.
What's your strategy?
Well, for me, I might just leave it alone. And if it gets to 10, so be it. If it gets to minus 10, so be it. I think those things are equally likely. So for me, it's like flipping one massive coin, or it gets to 10 or minus 10, which I guess is not looking great. The words yeah. So in chat, people might stop. Yeah, okay. We've got some numbers that they might stop at. Lily, do you so people's strategy is sort of
I would stop at -5.
-5? Yeah, okay, so the logic, I suppose, I'm not sure if we've done any maths yet, but the logic might be sort of stopping around -5. What's the reasoning there?
Well, if it's a real world situation, losing more than 5, but then you can ending up only winning 10 doesn't sound like a good deal to me.
Oh, okay. So you want to try and cut your losses, but you want to maybe still have some chance of winning 10. Okay, let's try it. I'm going to set it running. Rules for playing at home. Obviously, chat is not quite fast enough for you to shout stop and take the number. So rules at home are: if you see the large number there, say a number and you would like to stop, then you can just shout stop at home and write down what number you stopped at. So if you've got a strategy and you're planning ahead, you can maybe wait to see, is it going to get to my target number. For Lily, that's -5 or 10, I think.
Yeah.
Okay. And just to remind you again, everyone, it will stop at 10 or -10. So it's not unbounded. It will stop. Right, okay. I'm really excited to see what happens. Okay. Let's go. So actually I've set this to every half a second. So it started going up to 3. So if you were going to stop at 3, it just said 3, and you wouldn't be watching it now as it bumbles around 0 and 1 as it goes up and down. I bet you'd have missed out. Oh, there! If you were going to stop at 7, it managed to get to 7 there. 10. Right. Okay. Brilliant. Okay. So write down if you shouted stop at some point, you'll have written down a number for when you stopped it. And if you didn't shout stop, held your nerve, it made it to 10, you get to write down 10. We're going to play again. Lily's strategy is looking pretty good so far. Oh, hang on a minute. Off it goes. There we go. So this time it's going a bit negative. -4. I'm going to commentate over the top. -5, -6. So Lily, I think you've stopped, haven't you?
Yeah.
You've stopped because it got to -5. If you're stopping at Christian chat was stopping at -4, so Chris stopped ages ago. But look, it made it back up to 0. It made it back up to 0. So you're out because you've already stopped it. I'm still going. And there's some chance that it might make it back up, right? Oh, it's at -5 again. It's not looking great for me. We're going to play a few times, and I'm going to speed it up after this one. So Hector would have got 5 on the first game. This one, if you're waiting for a positive number, we've been waiting a while, haven't we? I wonder if some people in the chat there might be an effect where you sort of get bored. Oh, if you were waiting for a 5, then you get a 5 now. Oh my goodness. If you're holding up for 7, there's a 7. Oh, is it going to get all the way back up to 10 again? No, it's going back down to 3. There might be an effect where you might get nervous and you might change your strategy. Actually, not Lily. You got your -5 ages ago. I'm not sure that changing your strategy midway through the game. I think you might as well change it in advance. If in practice you'll get nervous when it gets to 5, then it's getting so close to that. If you were Sherry in chat has stopped because it got to 7, which is pretty good. Oh, my frame rate has just taken a nosedive, which is going to make this a bit more interesting. This one's gone forever. I did some practice runs before we went live, and the game does not normally take this long. Is anyone still playing? Maybe you're still playing. There we go. We got to 10. We got there. So at the end of that round, I write down 10, and Lily writes down -5.
Oh no.
Okay, we're going to play a couple more times, and I'm going to change that to pause that. And I'm going to change that to every 200 milliseconds instead. Reset it. This might go too fast to work. So Lawrence on that round stopped at -3. Sherry got 7. Hector stopped when it got back round to 0. So this is an interesting strat where if you're happy with it, 0. 0 is like starting again, though. Can we talk about that? I don't know. So I'm not saying Hector's wrong, but Hector says in chat, I stopped when it came back up to 0. And I think... tell me if this makes sense, Lily. When it's at 0, I want to see what happens next, because that's like starting the game.
Yeah.
I suppose that maybe it could be your strategy that gambling is evil and we should just take 0 straight away.
But then you lost your chance to win.
You will. If you're going to stop when it says 0, then sort of safety players don't always stop it immediately.
Yeah.
What was that? That was something falling over, I think. Right, good. Okay. Right, we're going to play a couple more times. The challenge is going to be at the end. I'm going to get you to, once we've played 4 or 5 times, I'm going to get you to add together your scores. Which at the moment for me is looking pretty good, right? But, right, okay, we'll see how it goes in a few more. Right, ready? Work out when you're going to start. Here we go. So this one's going a little bit faster. I hope that's coming through okay over YouTube. It's possible that it's only showing you some of the numbers, or it's giving me all sorts of error messages. Right, okay, possibly 200 milliseconds. It's only 5 frames per second. Okay, it's possible that YouTube has tanked down to -5 frames per second. While I was thinking about frame rates, it's at -10, which is quite bad for me. Lily, did you stop it? Where did you stop it?
-5.
Oh, I see, because it was going on its way down to -10.
Yeah.
Yeah, so that round I take quite a hit, -10. But then reset. You ready? Hopefully people have got a note of 3 numbers now. Here we go again. Off it goes. So this one's wobbling around 3s and 4s and 5s and 6s, or back down to 2s and 1s and 0s, and then negative numbers, and then -9 and -10. Okay, so disaster for me. It's run all the way down to -10. Did you stop it? Oh, did you stop it? -5. Oh, what's your high number? What are you waiting for on the high numbers?
I just...
Oh, you're waiting for 10, right? Okay.
Yeah, I'm looking for 10 and -5, so I felt like if I win more to compensate for my loss.
Oh, I see. Yeah. Right, okay. And this one obviously didn't make it to 10, it would have stopped. Yeah. So we're still, here we are. Right, okay, couple more, off we go. Oh, I'm supposed to click the reset button before I start it again. It's amazing what you can do in Desmos now. This one's going to quite large numbers. I think it's at 6 for a bit there. Very briefly, 7 or 8. Oh, and 10. Brilliant. Okay.
Yay.
Great. And then let's do one more. One more, off we go. So that one's straight up to 7. I think it might have got 7 pluses in a row at the start, which feels like we should win, except if you're waiting for it to say 8, then you'll be disappointed that it then went down again. And it's now around here, 7 again there. Still not 8 if you're waiting for an 8. And here it goes. 4s and 5s. This thing is memoryless. It sometimes feels like it's biased towards positive numbers, but as soon as it gets back to 0, that is like starting again. Oh, it did get to 10. Hooray! Okay. Right. At the end of that, I'm at a score of, I think we've done about 5 or 6 rounds. I think I might be at a score of 10 out of a possible 50. Lily, what's your total at the moment? Have you been keeping track? 15. That's all right. People in chat, what's your total? I think I've lost count a little bit. Have we done about 6?
Yeah, I think 6.
6, okay. I think I've got 10 or maybe 20. Joe's on 17. Anonymous person's on 27. Okay. Chris is on 16. But there's maybe a bias here that if you're on -30, then maybe you don't want to put that in chat or something. So I should allow for that a little bit. Okay. Obvious question is, I think, what should we set the numbers to win lots of points? And that is what I would like to do in this episode of the Ultra Online Maths Club. Right. Good. Oh, that's a 14. Yeah. Oh, you see, you get a little bit of time afterwards to see what it's going to do next. Yes, I suppose. Really, I should be forcing you to play in slow motion so that once it's gone past your number and you can see it's not going to make it to 10. should just stop there. Okay, so I think we need some notation. We've got a number line that goes from -10 to 10. We've got 0 somewhere in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, that's annoying. 1, 2, 3, 4, 5, 0. 0 in the middle. And I want to think about strategies where you stop at -a or stop at b. Actually, I'm going to make those look a little bit more different just in case they're different from each other. So these might be numbers where you say stop. A number that's so negative that you say, ugh, yikes, cut my losses. Or a number that's so positive that you think, oh, quit while you're ahead. Take B. So probably in chat, people had numbers for this. I think I saw people would tell me the kind of range of numbers they would let it run through. And for Lily, I think A is 5 and B is 10. Yeah?
Yeah.
I think it's good. Okay, good. And what we need to work out is something like the probability that you go from 0 via some sort of like up and down process, which I don't care that much about. It's exciting, but don't care that much. For the details, I want the probability. That one hasn't finished, so I should keep going. The probability that you get from 0 either to A first, -a first, or to B. Good. Okay. So I want probabilities. I'm going to write. There's all these points in between. Perhaps I'm going to write. What am I going to write? So it's important what number you're at, isn't it? I think I'm going to write Pn for the probability. It's a kind of sequence, depends on where you are. Probability that you see -a before B, given a kind of current value of n. It's the worst n I've ever drawn. There we go. Current value n. Maybe I should have typed that. Yeah. So you can do more complicated strategies where you condition based on what's going on. But of course, it's going to go through the numbers in order. So I claim that if your policy is wait for it to get to 7 and then stop if it says 8, that looks the same as just waiting for it to say 8, because it has to say 7 before it says 8. So I think you have this kind of, ultimately, your behavior is something like this, I think, unless you change your mind midway through. Okay. So yeah, Joe says -3, 10. Cherry's got a nice symmetric thing, -7, 7. Okay, I wanted to pause here before I go and do any maths on these probabilities to make sure that this makes sense to people. Can you let me know in chat if these probabilities make sense? I can kind of label them on here. We've got sort of P0 is your probability of disaster down here, and P -1 is the probability that you get disaster if it's already at -1, which feels like a bit larger, and P -a or something. We go all the way down here. These probabilities don't add up to 1. I know that probabilities sometimes add up to 1 when you've got like probabilities of different events, but these are, oh, what's the phrase? Sorry, Lily, you've done this more recently than me. What's the phrase for, I've got probabilities, but they don't add up to 1 because they're not describing that sort of event. What's that called?
Because we haven't. Wait, is it because we haven't considered all possibilities of the event, so that there is things that we neglect, so they don't add up to 1, or because they shouldn't be added because they're not about the same thing?
Yeah, they shouldn't. I think it's that they shouldn't be added because they're not mutually exclusive things. You could have probability that I have fish and chips for dinner, which is kind of totally separate from the probability that I win this game. It's sort of I guess you can literally add those numbers together, but they're not mutually exclusive. I can have both, winning and fish and chips, the dream. Good. Okay. Right. My challenge, I think, is that we want P0. Because the game starts at 0, and I want to know the probability of disaster. There's this effect that if you make A close to 0, then it's actually quite likely that you hit it. I mean, if you make A 1, so you're really averse to losses, if it starts going negative, you're like, ooh, -1, no thank you, then that will happen quite a lot. So it's kind of probability that you hit negative A before you hit B. Depends on what A and B are. Okay. Here's how the game works. So during the game, things change, right? So we have a 50% chance to go up or down. To go, so I'll write +1 or -1. So during the game, Pn, if the game is still going, so I suppose if n is somewhere in between -a and b, if the game is still going, then the probability that you hit -a is, well, 50% of the time it goes down to n-1, and then the probability would be the chance that you hit -a before b from there, and 50% of the time you go up, and then the chance that you hit -a after that is Pn+1. Woof. Right, quick pause. That's quite a complicated equation, right? I'm going to check with Lily if I'm making any sense, and also chat. You can just let me know in chat if I'm not making any sense. Chat, you know this. I'm trying to do something complicated here, to say something about the possibilities of what might happen next. You've got equations like this, I'm sure, in like the first year probability course.
Yes.
How would you explain that line of algebra that I've written down?
So imagine we have a probability for each step.
Mm-hmm.
So then we don't know any value, but think of them just as simultaneous equations. So then the probability for Pn would be 1/2 of Pn-1 plus 1/2 of Pn+1. And we can construct very similar equations with any probability and its neighbors, because we know this relation holds. But because we have this very nice relation, we can then try to solve it or do something with it that will help us to actually find out the value of the numbers.
Yeah. It would be nice, wouldn't it, if I could just write down Pn equals 3/4 or something. But the best I can do is to say, for now, is to say, well, find out what happens next. Maybe it goes up or down. Those are the possibilities, 50-50. And from there, well, the probability depends on where you landed. Good, okay. So that's an equation that, I like the phrase simultaneous equation, so I think that's really helpful, because we had lots of these P-1, P0 things. I should put more of them on this picture, right? P1 is over here. P2, well, I mean, its probability it doesn't physically exist anywhere, but P2 means from 2. Well, now it's looking a bit more like you're going to hit B before -a, so that probability will be a bit lower, probably. Good, okay. Someone in chat wants to know, have people been made offers for maths at Oxford with grade 7 in GCSE maths? I think the answer is yes sometimes, but usually people have got grade 8 or 9 in GCSE maths. There's a section of the UCAS form where your referee can tell us about things that were going on at the same time as your GCSEs, if that's relevant to you. Good, right, I've got an equation. My task for, apparently I've still got half an hour, we're going quite well for time, is to solve that. I need two more facts, right? I've got two more obvious facts because I said if n is between minus a and b, then you have this. So I should also do the kind of special cases. If n is equal to minus a, and if n is equal to b. And here is a chance for me to check that chat is keeping up, because here's what I want. I want the probability that you see minus a before b, given that the current value is minus a. This one's a bit easier. If the counter is currently saying minus 7, the probability that you see minus 7 before you see 3, it's already done that. So this one is 1. Maybe chat can tell me in the other case, if the value of n currently is b, if the counter is currently saying b, what's the probability that you see b before you see minus a? You're going to stop this process when it hits minus a or when it hits b. Okay, maybe chat can tell me that one, so I'll give them a second to think about that. Lily, you've said something about simultaneous equations, so now I feel like we should try and interpret this with simultaneous equations. I liked this one because it was very simultaneous looking. It involves related ones. What are we doing here?
I mean, simultaneous equations, we try to use them and get out the values. So if we know it's 1, I think that's a good thing.
Yeah, okay, even better.
Yeah.
I should write this p minus a is equal to 1, and p of b is equal to, well, chat's going to tell me what that one's equal to. So I suppose this is where it's slightly different from when we were actually playing the game in Desmos. I let it keep running afterwards, which is a bit mean of me. You get to see what you could have won, but it'll get to minus 10 or 10. Whereas, once you've stopped it, you've got to disconnect from it really to say, well, let's hit B. Chat's not going to join in, I think. So this one is 0. So if it's currently saying B, then well, it's made it to B. You're going to say stop, and you only get to say stop once. So if it's hit B, it's because you haven't stopped it yet. This is good news for you. It means the probability that it will get to minus A before B is 0. Good, yeah, okay. Cool. So these are different. If it currently says minus A, your chance of disaster is certain. And if it currently says B, well, say stop, that's your policy, is to say stop. And then your chances of disaster are 0 because you've now said stop on the good. Maybe I'll write that as kind of like PN measures your chance of disaster. Okay, so this looks like quite a fiendish problem because I've got lots of variables, all of these probabilities. They measure the way that if you're at a very negative number, getting close to disaster, then the probabilities over there are quite large. Larger the closer you are to disaster, but you see disaster before success. And over this end, I've got lots of variables for like 3, 4, 5, 6, and so on. But the probabilities over here are quite small, relatively speaking, probability of disaster, because it's quite likely that you just get a couple of pluses in a row or something, and you go and see success, shut stop beforehand. I guess this is A plus B plus 1 simultaneous equations or something. I've tried to count that. Gosh, counting is hard. Is it A plus B plus 1? Sorry, Lily.
Sorry, Miro is kind of lagging. Everything is
Oh,
blurry.
I'm really sorry. That is my computer trying to do too many things at once. Right, okay. I've got the simultaneous equation. You're
Yep.
there for that bit. I've now got the conditions that on the left, p minus a, which is a bit of a weird thing to say. That one's 1, chance of disaster, certain, it's happened. And on the other end, chance of disaster, pb is 0.
Zero. Yeah.
Good.
Okay.
I think it is several simultaneous equations. Depending on what you've set for your values of a and b at home, there are several equations there to solve. Luckily, the solution is a nice function. So I don't know. I don't know how to motivate this. You've done. I think this comes up in your course on. There's a first year course on probability. I can't remember what they say there. Do you? Do you remember anything? Or can you think of anything motivating to say? I'm going to show them the answer in a second for what all of these probabilities are.
I think that one of the easier way to think about it is I don't know if that's easier or harder, to be honest. But if you have all the simultaneous equations with you, and you just try to add them up and try to cancel things.
Ooh. Oh, I like that. I kind of think, yeah, now I sort of want to make people write them out. If your rules are stop at -3 or 7,
Yeah.
then you could write them all out. P minus 3 is 0. No, wait, P minus 3 is 1, sorry, it's happened. Disaster. P minus 2 is 1/2 of P minus 3 plus P minus 1, but you know P minus 3, that's 1. So it's 1/2 of 1 plus 1/2 of, I don't know the next one. So then P minus 2, you could write them all down and rearrange them and plug them all into each other. It sort of all zippers together until you hit the other end, at which point you know a fact at the other end as well. And then you can zipper back again. I like that. Yeah. So you can write down all the equations and try and solve them. Or, I don't know if this is going to fly. We'll give it a go. This equation says that each probability is the average of its neighbours. Add them up and divide by 2. So we're looking for a sequence where each term is the average of the ones before and after. So we'll have number, question mark, something else, and question mark is supposed to be the average of those two. If you think about plotting the values on a graph, this is quite hard to think about what the graph actually is, but I suppose it's n along here, the number line, and probability on this axis. So I've got my number line again down here from -a, where we've agreed probability of disaster. So this axis is Pn. And I've got my axis over here. Oh, I haven't put that at 0, sorry about that. So over here, the probability is 1. Down here at B, probability of disaster is 0. And in between, we want to find all of these other probabilities. Each one is supposed to be the average of the ones to either side. If you do sequences in A-level or equivalent, you meet sequences where each term is the average on the ones to either side. Another way to write that is that the difference between terms has to be constant. You can rearrange that equation on the board to say that the difference between these probabilities is constant as n changes. Or said differently, given a sequence, to fill in the gap in the middle, if you fill it in with the average, they'll lie in a straight line as you walk along. So our probabilities lie in a perfect straight line from 1 down to 0. If you don't believe me, you go and solve some equations, I suppose. We've got quite a lot of simultaneous equations. But yeah, it turns out to be linear, because each one is the average of its neighbours. And averages give you an arithmetic progression. Then the only question is, what's the coefficients of that linear function? and it's a linear thing that goes through 0 over here. So it must be some multiple of n minus b. Oh, do I mean minus? Guess I probably do. Oh yeah, no, I probably mean b minus n, don't I? Because it's got negative gradient. Some multiple of b minus n. And it's supposed to be 1 at negative a, so I'll divide it by b plus a. I'm doing this quite quickly to do the line. I'm trying to write down the straight line. The straight line that goes through b comma 0. So when you put in b, you're supposed to get 0. And goes through, when minus a in, we're supposed to get 1. I think I've got it right. I think it's b minus n over b plus a. Yeah, linear. There you go.
Yay.
Yeah, that's right. And you can even go and check this, right? So you can go check that it does this when you plug in minus a, check that it does this when you plug in b, and check that it really does satisfy this if you plug it in all 3 places. Oh, that's a bit of a mess. Algebra for homework, I think. In particular, so linear. In particular, P0 is just b over b plus a. Which is something like, so in words, oh, I don't know. Actually, I'm going to put Lily on the spot, sorry. I thought we could try and do this in words. I don't know. It would be nice to get words for this. So this is, I can't quite remember what we were calculating, but it's turned out to be b over a plus b.
Again, it's me with Miro lagging. So
this is probability that you hit minus a before you hit b.
Yeah, I see it.
And it's turned out to be b over a plus b, which I suppose in words is something like, can we think about distances to get to a?
Yeah.
B? What would that be in terms of distances then?
I mean, it feels kind of, it feels a little counterintuitive, but also it kind of made sense in the way that if you think about the distance from 0 to b to a and b,
yep,
that is the overall distance, right? So that's why we got a plus b at the bottom. Yep. And then we have b, which is just the distance from 0 to b.
Yeah. And the slightly counterintuitive thing is, this is the probability that you see a minus a before you see b. It's if b is very far away, if most of the distance in your range is getting from 0 to b, because you've set minus a to be very close and b to be very far away, then this probability is pretty close to 1. It measures.
Yeah. That's why I was very hesitant about my previous strategy when we were doing the counters, because if you think about it, it's more likely if it just moves 1 step up or 1 step down, it's more likely to end up somewhere near than somewhere far away.
Yeah, and now we can say how much. So I think your strategy was something like stop at minus 5 or stop at 10, and that splits. So starting at 0, that's a 1 to 2 ratio. So the ratio of distances, I'm supposed to look at distance to b is 10, total distance 15, because you're playing from 10, which means that we expect 2/3 of the time disaster. You see that first.
And if you multiply them up, you'll find out that they end up adding to 0.
Aha. Yes. Well, you're doing the expectation, right?
Yeah.
Yes, we should do the expectation. Let's do it in a second. I want to address Sherry's question in chat. So Sherry says, surely your A and B differ each round. I think it's n that's changing, the number that you can see in the big counter. And A and B, for me, they're the things that you set as your strategy. When will you say stop? When we played it before, you were allowed to change those between the rounds, but I'm trying to decide what the best strategy is. So for me, I think A and B are whatever your strategy is. I suppose I'm only considering strategies where you set those numbers and wait to see what happens. And other people in chat are considering more exciting things where you see what happens a bit and then make your mind up and decide when you're going to let it stop. The reason I'm not considering those is that from my point of view, watching you, that's the same thing. That you're going to say stop when it hits a particular number. Okay. So that's the probability you see minus A before B. The probability that you see B before you see minus A is, well, the other one, right? So this is B over A plus B. The probability that you see B before you see minus A is A over A plus B. So here's our result then. I'm going to type it, I think, so it's nice and large. Probability that you see minus A before B is, and it's B over A plus B. The probability that you see, and then I need to go B before minus A is, that's going to be A over A plus B. And then probability, I suppose, Lily's prompted me to think about what's the expected value, or the expected. So something like, we've got these things, they've got different values and they've got different probabilities. So, in this case, at the top here, you might see minus A with probability this much, or you might see B with probability this much. I can't remember what it's called, but there's a way to combine those together when you have like a biased coin or something, where you have these things with different probabilities, different values. There's a thing called expected value where you work those out. Oh, Jerry's on board, good. The thing that you do is that you multiply the value of the outcome by the probability that it happens, and you add those things together across your different outcomes. What's a real world example of this? Oh, I don't know. So you've got some probability of, I think I want a real world example where there's some probability of a good thing and some probability of a less good thing, and on average the right thing to do is to multiply and add. Yeah, so I suppose if I pick someone from chat, how nice is their day today? Because there's some probability that, some small probability they're having a 3-star day and some large probability that they're having a 5-star day. Then the average value is something like you multiply the probability by how many stars for each of the outcomes and you add them together. So there's sort of the total number of stars or something is like 3 times the probability that I pick someone with a 3-star day, plus 4 times the probability I pick someone with a 4-star day, plus 5 times the probability that I pick someone with a 5-star day, and add those together. Anyway, I'm being very slow at telling you that it is probability that you see minus A plus A over A plus B, probability that you see B as your outcome. A, that's B. Uh-oh, these things cancel, and that's 0. We should interpret this. Yep, so is it 0? Yes, it's 0. These things cancel out. Right, so you might expect that setting minus A to something clever and setting B to something very clever might increase your expected outcome. But the result is that nope. Always expected 0. Doesn't matter what your plan is. In the long run, if you play lots of times with the same strategy and add the results up, you'll get about 0. There's some variance that grows as you play. There's some variance on this, but you can't do better than just taking 0. If you don't play at all and just take 0 every time, and stop it straight away. Or if you go -10 to 10, then it's like 50-50 whether you see -10 or +10. It doesn't matter. Yeah. So result at the end. Can you play strategically to cut your losses or quit while you're ahead? No. Sorry, it wasn't a trick question. But it was a yes/no question. To which I don't know. Maybe that still counts as a trick question. I don't know. Good. Right. Okay. I find that quite surprising. That's got a name. It's called the optional stopping theorem, which says that in some circumstances, there's some terms and conditions on the theorem, but in some circumstances, no matter having knowledge of what's gone before, you might as well stop now in some sense. It doesn't matter. You can keep. Yes, okay, thought it was simplified to 1. Right, yes. The probability is up to 1. But yeah, it simplifies to 0 because it doesn't matter. So in this puzzle, there's no such thing as cutting your losses, and there's no such thing as quitting while you're ahead. That's a bit disappointing.
But
yeah,
maybe it's because we have equal probability of going both sides, right?
Yes, good idea. Tell me more.
Because in this case, we can have 1/2 probability of winning or like moving up 1 step, and 1/2 of moving down 1 step. But if we're more likely to move up, then it would seem very likely and reasonable that it's more likely that we'll end up winning some money instead of with 0, or winning something, not money maybe. And if the likelihood of going down is much higher, then it's also more likely that we'll have a very low and bad outcome.
Yeah, so you can do a version of this. Oh, I like this. So if you have a thing that's not 50-50, there's a version of this where you can still have a similar looking strategy. You might cut your losses or quit while you're ahead, but you would change these numbers, this 50% and this 50%, and then it's no longer the average, so it's not linear. You have to solve the simultaneous equations properly. So this is why I went for 50-50. I went for 50-50 partly because I could just say, this is just linear in the end. I'm going to redo that bit just in case anybody needs this. If you do this, so if you do, just to try and convince you a little bit more, I think I'm going to write this as 1/2 pn plus 1/2 pn on the left to make everything look a bit more half-ish. You know, it's comparable, right? I'm trying to tell you that something is the same on both sides. Okay, this is not quite the same on both sides. This is a funny trick to replace this 1 with a 50-50. And then you can rearrange it. So then I can move this term on the left and move that term on the right. And I end up with 1/2 of Pn minus Pn minus 1 is equal to 1/2 of, oh no, I've not done what I said I would do. No, I have. Pn plus 1, there were 2 Pn's, it confused me. That was the only thing I did and then it confused me. So this says the difference, okay, divided by 2, but the difference between probabilities at n, looking at the previous one, is the same as the difference at n plus 1. They have a common difference. It's a quadratic expression. Yes, okay. But that trick, so that's my trick. and it works because of the 50-50 in the question. Lily wants to change that. So if it's different probabilities and you're biased to go one way instead of the other, then you can't do that trick, and you have to actually go and solve the simultaneous equations. And I think in the first year Oxford course, I think they do that calculation for...
Yes.
Yeah. Well,
a bit too long for today.
It is probably too long for the next 10 minutes. But if you know, if you're doing A-level or equivalent, then you might see at some point tricks for solving second order differential equations with constant coefficients. You've seen this at A-level or equivalent, Lily?
I mean, well, we've done second order differential equations at Oxford first year course
Okay, right.
as well.
So I'm not being helpful. I'm saying that something in first year Oxford is a bit like something else in first year Oxford. Okay, fine. It's the same sort of theory as differential equations. Let's just leave it there. Good. Lawrence has got a different question. I should finish Lily's question, right? So if the probabilities are biased, then that does change the answer. You should let it keep going, I think, if it's going well. I'll let people do the calculations at home, I suppose. But if things generally get better, because it's slightly more likely to go up, then you should, I think, wait and see what happens. Let it keep going. Lawrence has got a question in chat on an infinite scale. Yeah, wouldn't you go for that's a good question. That is a very good question. So Lawrence says, what if you're allowed to have no minus 10, 10 stuff? What should you set it to? And I suppose if your policy, infinity's entered chat. So I suppose if your policy can't really be for it to go to infinity, because, well, you saw it in Desmos, it's not going to say infinity, is it? It's going to say some large number. So maybe for you, infinity might be something like 1,000,000 or something. And maybe this is counterintuitive, but we've seen that if you wait for it to get to either 1,000,000 or -3, then, well, most of the time it says -3 before it says 1,000,000. So most of the time you sit there going, another loss, write down -3. Oh, another loss, write down -3. But very occasionally you get a winning streak and then it hits 1,000,000 and you write down, amazing, brilliant, you write down 1,000,000. And the result that we've seen today is that you get quite a lot of -3s. On average, you get enough -3s to cancel out the winning 1,000,000 at the end. You get 1/3 of 1,000,000 times as many -3s as you get millions. So if I let you set the stop points further away from the origin, -10 and 10, the math still holds. You shouldn't take it to actually be infinity, because if you wait for it to actually say infinity, then you'll write down -3 every time. You can do probability questions on an infinite number line. There's a class of problems called trapdoor problems, I think, where, I don't know, does that mean anything to you, Lily? Maybe not. You gave me a look like it's not a thing. Right, okay. You're trying to run down an infinite corridor, and there are lots of trapdoors, one for every whole number.
Is it somewhat like the 3-door problem, or no?
No, there's no choices. There's just, it's like, I suppose, Squid Game or something, maybe. You're just trying to escape outwards, and there are trapdoors, and each one has got some probability, which depends on n of opening. Oh no. And you can set up the trapdoor probabilities such that there's some non-zero probability that you get trapped, and also some non-zero probability that you actually escape, which doesn't quite make sense as a process, right? Does it? Because, well, I have to define what I mean by actually escape, but some probability we keep going. Who do I email for more maths topics beyond the A-level specification? So for more maths, you might like other episodes of the Oxford Online Maths Club. We've got quite a few, possibly about 100 now. I've lost count. So you might like other episodes of the Oxford Online Maths Club. If you want to request an episode, we've actually got a plan for the rest of this season. But if you want to request an episode for some point in the future, you can email the email address on screen. And if you visit the Maths Club website, which is on screen and in the YouTube description, we've put a couple more suggestions at the bottom of the page for other things you might like. Good. If 100 episodes of this isn't enough for you. Other variations. I liked infinite grid, and I liked different probabilities for up and down. What else can we do to mix things up?
What if we have a more complicated simultaneous equation?
Ooh. So you can get those if it's allowed to change by more than one at a time.
Yeah.
So if it's got some probability of just sometimes going up by 2 instead.
Yep.
Nice. Yeah. So that would make the equations hard. And your policy might be to stop if it's at. I suppose your policy might be to stop if it's at B, or if it's somehow got past B by jumping past B. So if I'm waiting for it to say 7 and it goes from 6 to 8, well, that's all right with me. I'll take 8. Maybe you've got the question about whether you stop at 7. No, you've either got to stop or not, right? You've got to stop at 7 because it could go to 8, but that's always the case. But when it gets to 7, you've got to stop.
Because if we don't stop, we're back to the infinity problem again.
Right. So it's a bit like having a strategy. Having a strategy says at some point you can stop. It doesn't have to be 7, I suppose, but you can stop. Any episodes I recommend for engineering? Oh my goodness. Wait, let's look at the back episodes together. We're not really an engineering club. Not really an engineering club, but let's have a look at what we can find. Club website. Lily, while I'm looking for engineering episodes, in order to keep things on maths and philosophy, do you want to say anything about philosophy? We've been talking about people's intuitions about probability and sunk costs and like being stuck in.
There was actually something I wanted to say, but I haven't got the chance to now. We have been doing a course about philosophical topics in probability, and we were discussing what does probability really means and potential different types of probabilities. And so I know this might sound weird to someone who doesn't do philosophy, but they decide to differentiate between the idea of chance and probability.
Oh my goodness.
So chance is something that describes the potential likelihood of something, a natural event of like something that's observable. And we also have count, which refers to, like, say if we had 8, if we flipped a coin 8 times and the count we got for a number of heads and number of tails, that would be our count instead of a chance, because a chance is like something more hypothetical.
Oh, I see. This is the thing about if it's something that's actually happened, that's different from something that might happen. Okay.
Yeah, because you don't actually know about the hypothetical thing, right? How do you know if it's actually true, like you're thinking it is?
Yeah.
And it kind of goes nicely with hypothesis testing and stuff.
Don't take this as an insult, but this comes up when you talk about with probability with people from before A level. People's intuitions about probability before they've done probability at A level and had one particular way of thinking about probability taught to them. People have interesting opinions about what it means to say that something's got a 50% chance of happening.
Yeah.
Because it either will or won't, right? Maybe that's what 50% means. That it will or won't. Interesting. Right. Okay. Who asked for engineering episodes? Jessica asked for engineering episodes. I'm going to recommend two. One from last year, one from this year. Both of them with Maria. Maria came on to talk about music because Maria is a music student at Oxford. We talked about these numbers and tuning and Fourier transforms, which is really technical. Fourier transforms are important for engineering. That is my link. Also, it's a really fun episode. And then Maria came back this year to talk about maths of music and colour, where we talked a bit more about Fourier series and breaking down something complicated into its constituent parts, which is a good trick if you're doing electrical engineering, to break down a signal into its separate parts. If you like computer engineering, then you might like, where's it gone? Oh, I definitely have one in here. Projective geometry is quite fun because it's how you can get video game graphics to actually work. Miles came on the show and showed us some stuff in Unreal Engine, I think it was Unreal Engine, to demonstrate projective geometry, this effect that train tracks converge towards each other at the horizon. Cool. What if there's a probability that just goes to 0 again? Oh yeah, this is also good. Sorry, Joe's comment about it just going back to 0 again. There's a version of the trapdoor puzzles where the trapdoors don't quite trap you, they just make you start again. And then you can design those trapdoors to have some probability that you escape forever, some probability that you get stuck in a loop forever, and those are the possibilities. Right, okay, but enough trapdoors. I think we've hit 6 o'clock, so I'm going to stop there. Everyone shout stop. It's the end of the episode when we hit 6. Thank you very much, Lily, for joining in on screen and telling us about philosophy associated with probability.
And thank you to James for the amazing host.
Hooray! Thanks people in chat for playing along. We're going to be back in 167 hours for another episode of the Oxford Online Maths Club. Until then, it's goodbye from both of us. Have a wonderful afternoon. Have a wonderful weekend. We'll see you next week. Bye. Bye.